Hello everyone, it's me Gagan Kumar present over here to teach you physics. Let's move on to the video. Today we'll discuss Lenz's law and conservation of energy. So actually already we completed induced EMF, that is Faraday's law. So EMF equal to minus d phi by dt. Okay. So here this minus sign, a negative sign, that time I told it is basically comes from Lenz's law. What does it mean? That one will understand. So here remember Lenz's law, it gives basically polarity of the induced EMF. Okay. So what it gives? Polarity of induced EMF in a clear and concise fashion, that one will discuss. So what this law is telling basically? Now first statement you check. Now the polarity of induced EMF which is developing due to change in flux is such that it tends to produce a current which opposes the change in magnetic flux. Okay. So what exactly it is telling? Now suppose flux is BA cos theta. Suppose flux is this one. Now this flux is changing, suppose due to magnetic field. Due to magnetic field means, suppose magnetic field is increasing. Depending on time, magnetic field is increasing, suppose. Or by any method you are increasing the magnetic field. Magnetic field is not constant. If you are increasing the magnetic field, then flux will increase. That means there is change in flux happening. Initially flux was there, phi BA cos theta, but now you are increasing the magnetic field. Then what is happening? Now flux also increasing. So due to change in flux, induced EMF will produce. Now what Lenz's law is saying exactly? Now that induced EMF will produce in such a way that it will try to decrease the magnetic field. It will try to decrease the magnetic field. That means it will oppose the cause. The cause was increase in magnetic field was changing the flux. That's why induced EMF produced. But now induced EMF produced in such a way that it will try to decrease the magnetic field. That is the meaning of that negative sign. That's it. Now another example you take. Suppose you say due to increment of area, due to increase in area, flux will also increase. Suppose in a magnetic field constant, one loop is there, then area is increasing. Magnetic flux also will increase. Due to this one, induced EMF will produce. Yes or no? Now what will happen? Now induced EMF will produce in such a that, or induced current will produce in such a that current will try to decrease the area. Like that you understand. Or suppose, let's take example of magnetic field is decreasing. Let's take example of magnetic field is decreasing. Now suppose flux equal to BA cos theta. Now here, suppose your magnetic field is decreasing, then flux will decrease. So there is change in flux will happen. If a change in flux is happening, induced EMF will produce. That induced EMF produce means current will be there. That current will produce in such a way that it will try to increase the flux, or it will try to increase the magnetic field, because this is the cause actually. Magnetic field decreases, that's why flux decreases. So now current will produce in such a way that it will try to increase the magnetic field in that region. Okay, so this is what Lenz's law is saying. Okay, now in example in MCQ we will try to understand better. Now first one illustration you check here. So what it is given here? Now one coil is there. Suppose one coil is like this. Let me draw also. One coil is like this. Now one magnet is coming. So here one axis is given like this one. One magnet is coming towards this face of the coil, and north pole basically coming. What is coming? North pole. Now when north pole will come, what will happen? Now in this coil, more number of lines will go. it will pass. More number of lines will pass. Because from the north pole magnetic field lines are entering, right? Coming out, magnetic field lines are coming out. So when it will come close to this coil, then more number of lines will pass through the coil. So that means there is some increase in magnetic flux. Okay. So now what will happen? Now current will produce in this coil in such a way that it will try to oppose that. It will not try to increase the magnetic flux. It will try to oppose the magnetic flux or decrease in magnetic flux it will try. So for that purpose what? It should repel this. The coil should repel the north magnet so that it will come back, means more number of magnetic flux line will not pass here. So that's why what will happen? It will try to, how to repel this north pole? North pole can be repelled by another north pole. So that's why here one north like N like you do here, N like picture, then you give arrows like this. Let it call you do arrows like this, that means your current will be like this way. Okay, so this current is anti-clockwise current. So anti-clockwise current is forming here. Again I am saying try to understand. One coil was there, one magnet is coming. So from the magnetic field lines will be coming out. Now when the magnet will come near the coil, then more number of field lines will pass through the coil. Previously when magnet was far from the coil, that time no field lines were passing. So zero flux suppose. But when it is coming, some field lines are passing. That means there is change in flux within certain interval of time. So now that increase in flux, it will try to oppose. This word, remember, oppose word. Current will try to oppose that increase in flux. For what purpose flux is increasing? Now due to this magnet is coming, that's why flux is increasing. So that's why current will try to repel the magnet. If a magnet will not come, then flux will not increase. Okay. So the cause is magnet coming, that cause it is opposing. That is what the things you should understand. So that's why it is behaving like north. Suppose north pole is going away. Okay. Suppose north pole initially near the coil. Suppose here 10 magnetic field lines are passing through the coil. Suppose I am telling for example. Now what happened? Now when north pole will go away from the coil, that from 10, some 5 around magnetic field lines are not passing through the coil, because it is coming away means flux will that field lines will not pass through the coil. So there will be change in flux. Initially 10, finally 5. Suppose I am saying. Then what will happen? Now due to change in magnetic field lines, number of magnetic field lines through the coil, flux is changing. Then what will happen? Now this current will produce in such a that it will try to oppose that. So it will try to increase the flux, or it will try this magnet to attract. Who is trying this? Now induced current is trying to magnet to attract. Okay. So how to attract north pole? To attract north pole you need a south pole. So that's why here you do like S like picture, then arrow mark you give, and in that arrow mark you give the direction of current. So here what is coming now? Current, clockwise current. Okay. So like this you have to understand. So when north pole is coming, coil is repelling. But when north pole is going away, that time this coil is attracting. So this is the thing you can remember. Okay. So that means what is happening actually? Now this current is producing a magnet. How current will produce a magnet? Because before already we studied a circular current carrying wire will behave like a magnet. How? See this picture correctly. See this picture correctly. Here one magnet is coming, suppose north south. Magnet is coming means here what will happen? Now here this coil will produce another magnet like this. Okay. So this side will be north, this side will be south. Okay. This side will be north, this side will be south, so that it will repel the magnet. If north pole is coming, then this coil is behaving like a magnet and it is repelling. So to become this north pole, you know, current, how should produce current? Now current should be in this way. Current should be in this way. According to right hand thumb rule, you can say, okay, if current is going like this way in a coil, like this way it is going, then all magnetic field lines will go away like this and it will enter here. So that means definitely this is north, this is south. Okay. So remember, magnetic field lines due to a circular coil. Okay, so with that consideration we are doing here. So if a north pole is coming, then this coil is acting like a magnet, bar magnet, and that north pole is towards this north pole, so that it is repelling back. Okay. So if its south pole is coming, then also it will behave like a south, then current direction will change. Current direction will change. Okay. So like this you have to understand about the Lenz law applications or MCQ questions. Okay. And another thing, try to understand, this Lenz law is accordance with the conservation of energy. Why it is like that? Because suppose a coil is there. In this coil, simply you are bringing a magnet, and in this coil you are producing the current. Okay, this is what you are doing exactly. So what you are doing, a magnet you are bringing, so then in this coil a galvanometer there, suppose galvanometer there, now some current you are producing. That means there is no battery, no external supply, just simply you are taking a magnet and you are producing the current. Okay. So it is like magic, like you are doing, right? So actually what is happening now, when you are bringing the magnet, so you are doing some work actually. So that work is basically mechanical work. So you are doing the mechanical work. That means some mechanical energy is there, that is getting transferred to electrical energy. Why I am saying electrical energy? Because you are saying that in this coil some current is producing and some EMF is there. So that means this is about electrical terms. So electrical term it is converting. And you know, energy is always constant. It will get transferred from one form to another form. That is the conservation of energy. So that is what it is happening here. Okay. So Lenz law says also basically what? Conservation of energy is happening in this Faraday's law, or you cannot produce like magic, you cannot do. Okay, you cannot produce current like this, how magicians produce fire immediately like that. It's not like that. Okay, when you are moving the magnet like this, my hand is doing some work. Okay, my hand is doing some work. So mechanical work is done. Okay, so that energy is getting converted to electrical energy. Okay, and that also in wire, what is happening? Heat producing. If a current will be there, resistance will be there, then heat will produce. Then electrical energy will get transport to heat energy. So like this thing is going on. Okay, so energy conservation is there. So you can write Lenz law is in accordance with the energy conservation. Energy conservation. Okay. So you write this Lenz law statement, you write, then after do this picture as an illustration, and little you want to explain, you explain. Okay. Now next, understand some MCQ based on this Lenz law. Based on this some Lenz law, understand some, explain. Okay, you want to write here, just a little write here, notes, one notes you can. Or notes you can give. Your EMF equal to minus d phi b by dt, d phi by dt. Okay, or you can write also sometimes EMF equal to minus n d phi by dt. Okay, if n number of terms are there, then this is the formula, or if single term is there, then this is the formula you can write. This negative sign basically indicates about the Lenz law, and one star mark point you can write Lenz law in accordance with the conservation of energy. Conservation of energy. Okay. So this much things you remember. Now remember here one question is coming. The polarity of induced EMF is given by which law? Ampere's circuital law, never correct. Biot-Savart law, never correct. Fleming's right-hand rule, it will be never correct. So just now we studied, okay, here we studied here polarity. Polarity of induced EMF is given by Lenz's law. Lenz's law is a consequence of conservation of what? Conservation of energy. So these all options are incorrect. Conservation of energy. Now which of the following statements is not correct? Whenever the amount of magnetic flux linked with a circuit changes and EMF is induced, it is correct. When magnetic flux changes, EMF is induced, this is correct. The induced EMF lasts so as long as change in magnetic flux continues, yes. So induced EMF, there still change in flux is there, okay. That is also correct. These two statements are correct statement, but in the question they asked what is not correct. Now the direction of induced EMF is given by Lenz's law. Yes, the polarity or direction of induced EMF is given by Lenz's law. Already we discussed this statement also correct. So definitely for this question, this will be answer. This statement is not correct. This statement is not correct. Lenz's law is a consequence of law of conservation of energy, but it is given momentum. So this is not correct. Okay. Now in the given figure, current from A to B in the straight line wire or a straight wire is there, is decreasing. Now the direction of induced current in the loop. So what they are telling, here current is there, suppose I current is there. Now this I current is decreasing. So current is decreasing, di by dt happening, right? Okay. Then what will be the direction of induced current? Now you can say, sir, in the flux we have magnetic field, we have area, we have cos theta. But current you did not say anything. We told you. Current, we told in Biot-Savart law. Magnetic field is nothing but it is mu naught I by 2 pi d. Okay, for a straight wire. This already we have. Mu naught I by 2. That means in flux indirectly current is there. Current is there inside a magnetic field. Now if they are telling what? Current is decreasing. If current is decreasing, magnetic field also will decrease. So decrease in magnetic field will decrease the flux. So that means there is change in flux happened now. So definitely there will be induced current. Definitely it will be there. Okay. Now next, how it will be, clockwise or anti-clockwise? Now to understand that, first to get the point here. Due to the straight wire, what is the magnetic field below and above? How it is? Now keep your thumb in the direction of current. This all fingers will enter here. All fingers are entering here means this is the cross magnetic field. And here it will be dot magnetic field. Okay. So now you have to understand. Inside this dot magnetic field, what do you mean by dot magnetic field? Now magnetic field is coming out. Magnetic field is coming out. If a magnetic field is coming out, then what is happening? Now this magnetic field is decreasing and coming out. Here direction of magnetic field is coming out. The magnetic field is decreasing because current is decreasing, right? So I told you, if magnetic field is decreasing, then induced current will produce in such a that it will try to oppose that. So decreasing opposition is basically what? Increment. So it will try to increase that. So how to increase? Now it would produce what? Now induced current in the circuit to produce a magnetic field. Suppose I am telling this induced magnetic field. In this region it will produce a magnetic field A which will have a dot. Now you say for a circular coil, current in such a that magnetic field is dot. So how the current will be? Now current will be like this. This type of current can produce only what magnetic field? Now dot magnetic field in the region, in this region. See, this is the magnetic field due to this one. But now induced current will try to oppose the cause. So that's why induced current is producing such that it is inducing another magnetic field which is increasing the magnetic field. Okay. It is producing because both dot means field will increase. Okay, so it is opposing the cause. So here anti-clockwise. So what is the direction here? You check here. This one is anti-clockwise direction. Okay, remember this way direction is clockwise. This way clockwise. This way anti-clockwise. Okay, so remember that. Okay, so always you check what is given. Current is decreasing. In which side this loop is there? If a loop is below this, something differently you would tell, you would analyze. Loop is where you check, here where is like this one, here left side, right side, you check everything correctly. Okay. So always remember, you check inside this loop what is the magnetic field due to straight wire, dot or cross. Then after you check current is decreasing or increasing. Current is decreasing. If current is decreasing, field also will decrease. If field decreases, flux decreases. So now induced EMF will produce in such a that it will oppose the cause. So field is decreasing, right? So it will try to increase the field. How to increase the field? Now here if a dot field is there, one dot field is there, another dot field is there, then what will happen? The magnitude will definitely increase. So that's why the induced magnetic field happened how? In that region, that is in a dot. You understand this, then after you give the direction of induced current, then after you erase this noise. So you understood that direction of induced current is anti-clockwise. Okay. I hope you understand. It takes little time to understand because there are many steps are there involved. Small steps. First is picture. From this picture, how current changes, how field changes, how flux changes. Then it will try to oppose. In that way, you have to calculate. Okay, or you have to say. So steps involved, you understand clearly from the language whatever I am saying. Okay.